Thank you, Andreas, and thank you, Simon, for, well, he's distracted now, but for inviting and organizing this. Okay, well, as Andreas just mentioned, I'm going to give the 4 lectures here on the topic of LSCC. And before I do that, actually, I want to just give an invitation or a bit of a sales pitch. So I now work at an institute in the United States called Southern Illinois University. And it's located in Carbondale, Illinois. And for those of you who don't know where this is, and actually a lot of people probably don't, if I'm not the greatest artist, but so here's maybe a rough map of the United States. And, well, okay, so here's, say, the Great Lakes are somewhere, something like this. And if here is Chicago, Carbondale is at the very southern part of the state. Here's the state of Illinois, and St. Louis is over there. So the reason I'm telling you this is I'm currently in search of graduate students. And if you guys are interested in this and are wanting to study it further, you can email me. And this semester, actually, I'm on the graduate committee, so I have a little say in who gets admitted. And so I'm sure all of you would be just fine in that. So this is just a brief sales pitch on that. OK. So on to the science. All right, well, I'm going to be giving 4 lectures. And I'll just describe where we're going. So the first one today will be introducing LSCC. And we're going to go over a bit of the formalism. So of the 4 lectures, this will probably be the most abstract because we really just want to lay out a framework of what LSCC is. And then starting tomorrow, we'll look at specific problems, LSCC problems. So there'll be 2 lectures on state discrimination. So this will be part 1. And then the third one will be, part 2. So in part 1, we'll just look at 2-qubit systems. And we'll work out the full solution to 2-qubit discrimination by LSCC. And then in the third part, we'll look at a new class of problems known as asymptotic discrimination by LSCC. And I'll describe why that is, and I'll give a little motivation for why it's an important question. And then in the 4th lecture, we'll look at another class of problems known as entanglement transformations. OK. So if at any time, of course, just if you have a question, raise your hand, stop, and we can, and I'll be happy to try to answer it. All right. So I want to begin today by thinking of a very specific problem. It's going to sort of motivate the whole subject of LSCC. And well, all right. So just imagine first that you are given one of 2 possible quantum states. Okay, so you have some system, and it's been prepared in either psi1 or psi2. And we know that if these are non-orthogonal, then you'll never be able to perfectly determine which state was prepared, whether it was psi1 or psi2. And actually, as one of the exercises or something, you guys can try to prove this. Did I lose the mic? No. OK. So this may be the first sort of exercise to go through. Right. So this is something that is really a property of quantum states. I mean, if you were talking about distinguishing classical states, you wouldn't have this because you don't have a notion of non-orthogonality in classical systems. So this is really a true quantum property. OK, well, you can imagine now that if you added a third state, a third non-orthogonal state, and you wanted to try to distinguish these, it would be even more difficult. OK? And of course, you can ask, well, what do you mean by distinguishability here? We need some sort of measure of success. And so for most of the lecture, we'll just, actually all 4 lectures, the figure of merit will be something known as the optimal guessing probability. Okay, so you're going to make a guess on whether psi 1, psi 2, psi 3 is prepared, and with some error, you're going to guess incorrectly, and your job is to minimize that error. Okay, so as a concrete example, probably the easiest or simplest pair of states, so we'll call this T0, T1, T2. And this is the double trine ensemble. And it's the simplest because it has a high degree of symmetry. Okay, so these are 3 non-orthogonal states. And if the way to visualize this is if you looked at the block sphere representation of this. So here, this is the xz plane. And so the 0, this is going to be T0 here. And now we're just going to rotate about that by 120 degrees, and we get T1 is, let's see. Well, okay, I mean, I guess the overall phase doesn't really matter. Oh, no, that was right. Like this. So here's T1, and here's T2. Okay, so this is known as the double trine ensemble. Oh, sorry, the single trine, not the double trine. This is the trine ensemble. We'll get to the double trine in a second. All right, and so one challenge exercise would be to try to determine the optimal measurement for distinguishing these 3 states. So you're given one of these, and you want to try to minimize the error in identification. And so what is the minimum error probability, and what does that measurement look like? Okay, so far this is just a single system problem. In fact, it's just a single qubit problem. But now we want to add some complexity to it. Now what I want to imagine is that we have 2 copies of each state. Okay, and what we're going to do is we're going to separate the copies to 2 parties. We're going to call them Alice and Bob. So Alice will have the first copy. Bob will have the second. And we're going to separate them. They're going to be in distant laboratories. And now the question is, what is the optimal distinguishing strategy if they're separate? Okay, so there's 2 copies of each, and Alice has 1 copy, Bob has the other. They're in different systems, and the constraint is that they can only perform measurements on their local system. Okay, so now this is the double trine. Double trine ensemble. And this problem was studied by Asher Perez and Bill Wooters in '91. And this is probably one of the first LOCC papers, this Perez and Wooters paper, where they really are asking about performing a task in distant laboratories. Okay, and so let's study this a little bit. So I'm going to switch over to this board. I'll move back and forth a bit. Okay, well there's maybe 3 different strategies that Alice and Bob can use to distinguish these states. So the first would be the following. So I'm going to draw it like this. So imagine now that here's Alice's wire, this is Bob's wire, and originally they're given state Ti. So they don't know what it is, but they're given one of these states. All right. And they're in distant laboratories.
Same state?
Yes, the same states, right? So they're given one of these, all right? So they're perfectly correlated states. All right, so in the first scenario, let's assume that they have this additional resource, so they're separate, but they also have access to a quantum channel from Alice to Bob. So Alice is able to send Bob a quantum system. Okay, so we're going to denote the quantum channel by a solid line there. And what Alice is going to do is she's going to send her copy of TI to Bob, and then Bob is going to perform some sort of measurement on both the copies, and then he's going to make a guess. So essentially, what we've done in this situation is we've sort of dropped the distant lab constraint, right? Because essentially the problem is just this, and Bob has access to both copies, and he's just going to perform some global measurements on both the copies. Okay, so that's one scenario. Another scenario would be.
Eric, I have a question.
Sorry.
I have a question.
Yeah, sure.
In LOCC, I thought CC was for classical communication.
We're going to get there just right now. Yeah, I'm setting this up so we can compare the differences between classical communication and quantum communication.
Oh, okay.
Yep.
So that's not LOCC.
No, it's not.
Okay.
Okay. In scenario 2, again, they each have their correlated copy. But now the situation is exactly as Simon mentioned, is that now they don't have access to a quantum channel, and all they have access to is a classical communication channel. But we're going to take it one step further. We're going to constrain them and assume that it's just a one-way channel. Okay, so only Alice is able to send Bob classical communication. So the way this would work is Alice would make some measurements on her copy, and she would send a classical message to Bob. Okay, so the double lines indicates classical communication. So she's going to call him up on the phone. She's going to email him something. And then Bob, on his end, is going to make a measurement. But he's going to use that information that Alice sent him to decide what particular measurement to make on his copy. And then he's going to make a guess. Okay? And now the third scenario is again where they're limited to classical communication, but it's no longer a one-way channel. Okay, so now we're going to allow feedback between Alice and Bob. And so here it would look something like this. Here's Alice, here's Bob. And so we're going to assume that now Bob can give some feedback to Alice. Now she can perform another measurement. Broadcast her, tell Bob what she measured her in the second time. Bob will perform another measurement, and this will go on indefinitely. All right, one thing to note is that in this, so you see here, what we're assuming in this scenario is that Alice is going to make a hard measurement. Okay, so when she makes her measurement, after which her state has collapsed down to some defined state. Here, these are weak measurements because we want to be able for her to make multiple measurements on her system. So these will be some sort of weak measurements. So there'll be some sequence of weak measurements.
Can you repeat that?
Sorry, this is a weak measurement.
No, I mean the entire thing. So what's the hard measurement? What's the weak measurement?
Okay, so, well, all right, maybe the way to see it would be like this. So a hard measurement, hard. Would be something, so I'm gonna use this terminology. I'll define it a bit later. This would be, it's a POVM where the elements rank 1. Okay, so essentially, the way to think of this is, so if here's your POVM, something like this, here are your POVM elements. Alice performs this measurement, and then it's collapsed into one pure state afterwards. A weak measurement is not of this form. So it would be you'd have some non-rank 1 POVM element.
But there could be rank 1 POV measurements as well.
Yes, there could be. Yes, right. Okay. All right. So in this paper, this Pears-Wooters paper, call this the PW conjecture. Is that of these 3 scenarios, 1 is strictly greater than 3 is strictly greater than 2. So what I mean by greater than, it means in terms of your ability to distinguish these 3 states, 1 is the strongest scenario. You can distinguish best if they have a quantum channel. The next strongest is 3. And of course, 3 will always be greater than or equal to 2. I mean, because 3 is a generalization of 2. But what they actually conjecture is that these are strict inequalities. Right? So you can always do strictly better given more resources like this. Okay, and so this conjecture turns out to be true.
The conjecture only for these states?
Yes, for these states, right? Yes?
Does even increasing the number of rounds in scenario 3 help?
Yes. Yes, it does. So, okay, so when I say this is true, what it can show is that if you consider a 2-round scheme like this, where Alice gets some sort of feedback, this is strictly greater than the 1 round. Okay, and but if beyond this, it's still open. So the optimal scheme is not known. But what can be shown is that if you allow feedback, you can do strictly better than just a one-way channel. Okay.
So I think another one is not known.
Well, it's not known. Okay. I think it is. Yes. Okay.
For all symmetric and symmetry?
No. Well, probably. Sorry, who asked the question? Yeah, I'd say probably, but the proof techniques are very specific to just this ensemble. Whether this holds for all symmetric ensembles. Mm-hmm. What we'll see actually on Tuesday's or tomorrow's lecture is that if you really need 3 states. So if you had just 2 states here, then actually then 2 is equal to 3, and it's also equal to 1. Okay, so that's what's sort of surprising. So you really need the 3-state ensemble to bring this out. Yes.
To the first part of the conjecture, 1 greater than 3.
Yes.
You have to prove for infinite feedback.
One.
You do.
Yes, you do. Yep. Mm-hmm. And there are ways of sort of dealing with that. Okay. Yeah.
Here the quantum channel was the identity channel.
Yes. Yeah. Noiseless. Send it through. You get it out. Exactly. Yes. Okay. So I think as the story goes, actually, this is what Gilles Bressard told me that this paper in '91 was published, and they got together to discuss it. Charlie Bennett and Gilles and others, and it ultimately led to the teleportation paper. And the way it goes is, again, as I was told, is that they were trying to sort these different scenarios out. And one of the fellows asked, well, what if Alice and Bob had access to an EBIT, or a maximally entangled state? So how would that change things? So we're going to consider another scenario where Alice and Bob also have a maximally entangled state with them. Let's see. Should I draw it? Or should I do it? Yeah, okay. I'm going to draw it right here. So suppose now that they have some state, and this is is just a EPR state. Okay, so here's Alice and here's Bob. So this is some additional resource they have. And now they're given their state Ti. And what's going to happen is they're going to use this in the following way. Alice is going to perform some measurements across both her half of the EPR state and her Ti state. And she's going to communicate it to Bob. And then Bob is going to perform, say there's some unitary here. He's going to perform some error correction, essentially, on his half of it. And what comes out after he performs this controlled unitary is Ti. And then he performs a joint measurement on both the Ti from his original half of the EPR state, and then he performs some guess. OK, so this is essentially, this is the teleportation scheme here. Because what's happened is Alice and Bob have used their EPR state, and Alice has teleported her copy of Ti. And so now Bob receives it there, and then he's able to perform a global measurement across both of the copies. So you see, this scenario, I guess we could call this 2 prime. This is equivalent to 1 in the following sense, that they each start off with a copy of Ti, and in the end, Bob is performing a global measurement across both copies. But the difference is that they need this EPR state, right? So I guess if you wanted to think of it, you can like view this. If you just wanted to put a box around this, this is essentially a quantum channel, right? This box is effectively performing this, the quantum channel there. Okay, and this I think is a really important fact, and so I'm going to write this out. So local operations and communication plus EBITs gives you full quantum operations. Okay, so this is sort of the resource equality here. So local operations and classical communications, that's essentially what's going on here. Alice and Bob are performing local measurements, and they're communicating classically. There's no quantum communication going on here. But they also have the EBIT resource. And when they have this, they're able to recover full quantum operations. It's as if they had a quantum channel. And so Bob can measure globally.
So quantumness comes from phi.
Yes. This guy. Yes, exactly. Right. OK, so this local operations and classical communication is, of course, the acronym is LOCC. And so we refer to this LOCC as always keep this sort of paradigm in your mind with local measurements and classical communication.
So in the first case, Alice was not performing any measurement at all. But in this case, Alice does.
Yes. Yes. Yeah, someone up here mentioned it. This is just sort of like the identity channel. I mean, she's just sending it over. OK. So now this is interesting because the question becomes, all right, I mean, the number of EBITs you would need to actually recover full quantum operations could be quite large. I mean, here we had a bit of a trade-off. We said for one of these maximally entangled states, we could teleport 1 qubit state. Okay, but if you have larger systems that you're dealing with, you're going to need more EPR states. So a very natural question then is, well, what can you do if you limit the amount of pre-shared entanglement you have? And to the extreme would be, what if you had no pre-shared entanglement? So we want to get rid of this completely, and then we can ask, what is possible for Alice and Bob to do? And this is essentially the subject of LSCC. This is what it's studying, is that if we limit the amount of pre-shared entanglement, including the extreme case of no pre-shared entanglements, what sort of information processing, what sort of tasks can Alice and Bob accomplish? That's the, for the overall subject there. Okay. Any questions on that? Because then this was just sort of the introduction, motivation of why we study this. All right. So now to really understand this and to move beyond and prove things and calculate limits and rates, we need to be able to characterize the set of LSCC operations. And so what we're going to do now is work out some of the formalism. Okay, so this would be LSCC formalism. And the approach we're going to take here is we're going to discuss LSCC in terms of something known as quantum instruments. And so what we'll do in the next maybe 20 minutes or so is I'm just going to give an introduction to what quantum instruments are. And so it's general, and then we'll move specifically on to LSCC instruments. Okay, so this would be just like a subsection introduction. So this is, say, quantum instruments. And various representations of CP maps. CP meaning completely positive maps here. So I'm going to go over some basic things here, just because I'm not sure the full background of you guys. If you're getting bored and everyone says this is easy, just like start waving me ahead and we can skip. Or if you want more details, just let me know as well. All right. Okay. So what we're going to do is, maybe I'll start up here. So we'll let H denote, this will be our underlying Hilbert space. Okay, so this is going to be the space that our kets live in. These are the state space of our system. And then we'll write pos 8. This is POS, and this is going to be the set of positive operators acting on H. And by positive, it's just think of this as these have non-negative eigenvalues. All right. And then I want to let, say, D of H. This will be the set of density operators. Acting on H. Okay, so I mean the way to think of this is H is where your pure states live, all right, and then your density operator are your mixed states, okay. And the difference between pos 8 and this DH is that these are all trace 1. Okay, so as we know, the density operator is a positive operator whose trace is 1. So this is a subset of this. All right, and then actually we need one more. So I'm going to write CP. This is going to be the set of completely positive maps acting on our pause 8. Okay, so what is a completely positive map? Well, this is sort of a central idea in quantum information, is that a map, call this E, is CP if we tensor E with the identity and we act on some entangled state, that this will be positive as well. Okay, so let's break this down. So according to our definitions here, E is mapping pause 8, pause H. And now we think of, actually let's make this a pure state for simplicity. So we put in some entangled state. Okay, so psi now, this is going to be on some entangled state on 2 copies of H. And we act on, our map E is going to act just on the second copy of H, and the identity is going to act on the first copy. And what we require is that this, whatever comes out of here, will be non-negative. Okay? So this is what it means if it's CP. And the idea here is, why are these important? Is because these are what preserve density matrices, right? So we want to think of our maps that if we act on a density matrix, we'll get a density matrix out. And we want that to be the case even if our original density matrix is entangled with some other system. That's why we need to we tensor on the identity, and we imagine that this is acting on some joint system. It's acting on 1/2 of it. But we want whatever comes out will also be a valid density matrix, meaning that it's positive and trace 1. So that's why this is of interest. Okay. Right, as the title said, we're going to study various representations of CP maps. Yes?
CP, does it contain in DH or DH contains in CP?
No, this is maps acting on DH. So it maps an element of DH to an element of DH. Okay? Right, good. Okay, so yeah, as I said, that we're going to look at 2 particular representations of CP maps. The first is known as the Choi representation. All right, and so essentially, what is true is that we have this isomorphism between the set of completely positive maps and the set of density operators, or let's just say positive operators that are acting on 2 copies of H. Okay, so this is what we're going to show. I'll sort of outline this isomorphism. But again, the idea is that maps acting on the set of positive operators, completely positive maps, is isomorphic to the set of positive operators if we consider 2 copies of H. All right? And the way this works is you set up this mapping is, okay, so let's define phi to be, this is going to be an unnormalized state, and it's going to be basically, this is, you think of this as an unnormalized maximally entangled state across 2 copies of H. Okay, so we're thinking of 2 copies of H, and now this is a maximally entangled state across 2 copies. Right, and So the way this works is for any epsilon in CPH, we define this operator. So this omega operator. Now this is a density operator, and it's obtained as follows. So we take our state phi here, and we act on it 1/2 by our map E. And what we get out is a positive matrix. And why is it positive? Well, because by assumption, E is CP. And therefore, when it acts on even 1/2 of an entangled state like this, we get out a positive operator. OK, and so this is showing that for any element in CP, we get an element in the set of positive matrices and 2 copies of H. All right, so now we can look at the reverse mapping. So conversely, right, so if this omega is in, OK, so now we're given some positive operator. Now we want to define a map, right? So we want a way to map back, and we define the map as follows. So we'll define it using this action. OK. Right. So the way this map works is you put in some state rho, and you take the transpose of rho. So you assume when you take a transpose operation that you fix some basis. OK. The transpose operation is, so this is with respect to some basis choice I. And then what we do, the tracing out. This is a partial trace here. Then what we do is we consider this product with omega, which was our original density matrix, and we trace out the first copy of H. And what comes out is then the action of this map. OK? And so I guess as one of your homework exercises will be to show that actually this is the inverse of this mapping. So let's say exercise would be to show that the map E is OK. And so why is this? Well, yeah, we'll just leave it as the exercise. OK, any questions on that? This is the Choi representation. And so the other representation, which probably you guys are maybe more familiar with, is a Krauss representation. Okay, so this is the all right. So the first thing to note is that if you start off with this equation here, OK, this is actually, we can think of this as a linear map. And the way the linear map works is that if we input a basis element, say I, j. OK, so remember, this transpose is defined with respect to basis I. So now I want to input this element ij. And if we look at what this is, we take the transpose of that. It gives us back ji. Okay, and so now we're actually we're going to evaluate this. And the way we're going to do it is because this is a positive operator, it has a spectral decomposition, right? So we can write omega as some sum so here these are unnormalized. I've absorbed the eigenvalues into the kets there. And then what I want to do is I want to define a map. And the way the map's going to work is it's going to send element I to I RK. Okay, so now we need to be a little bit careful in interpreting this. So these RKs, remember this omega is living in this space, right? So these states RK, actually we should write as, say, H1, H2. Right? These are bipartite states. And here this is just I. This is just a single copy, so this is an H1. And so then what we're, H1. So then what we're doing here on this, the right-hand side, the way we interpret this, is this is like a partial contraction. Right? So this is some state that's living in the bipartite space, H1, H2, and we're contracting it just on the H1 side. And, okay. And so then because this is actually a linear mapping, that means that we can represent the map with a matrix MK. And so this acts on I, and it gives us back I RK. Okay, so that is sort of the map we've defined. Now, substitute omega into here. And then what you'll find is when you take this partial trace and using this definition of the map, then you get that this is equal to sum over k of your input, ij. Okay, and so then we just, so this is its action on any basis element ij. All right, now we're going to extend by linearity, and we have the full action of the map is given by this. Right? Okay, so these operators, MK, are known as Krauss operators. So the MK are Krauss operators. Of our map E omega. So we have now two ways to represent our CP map. We can talk about its Choi matrix, or we can talk about Krauss operators. Yes.
It maps H1 into H2.
Yes, it does. Yes.
And then you use the identification of H1 and H2 in the next step.
Yes. Yep. Very good. Yes.
The restriction on MK only, they are only linear operator.
Yes, they are.
Only this.
Yes. Yep. Okay. All right. So now with that, then we can talk about what instruments are. Okay, so a quantum instrument is just a sequence of CP maps. Oops. Such that if we sum up this is trace preserving. So actually, we're talking about a very specific family of quantum instruments here. These are discrete, and then in the sense that we can count the number of CP maps. And also, we will always assume that the instrument, this is an infinite sequence, and we can always just add zeros. If we want to only talk about a finite number, we just pad zeros. But so this will be a true infinite sequence here, countably infinite. So that's hence this notation. And we also assume that this converges. So there's an assumption in that this exists, this series here. And so it's a sequence of CP maps such that the sum is trace preserving. Okay. So what is the interpretation here? What are we thinking? Well, the idea is that when we deal with instruments, it gives us a nice way to combine both a quantum output and a classical output of a measurement in the following sense. So when we perform instrument J, so I'm going to use this big curly J to always talk about instruments. So when you see that, you think of that as the sequence of CP maps. So if we perform our instrument on some state rho, then we obtain rho goes to E lambda rho over trace E lambda rho. And we learn the value lambda. And this occurs with probability p lambda. And this is just the trace of E lambda rho. Yeah, OK. So again, the idea is that we perform our instrument on our state rho. What we get out two things. The first is that we get out some post-measurement state, which is this here. But we also learn the measurement outcome. So we learn lambda. So there's two things we get out of it. And of course, this is some stochastic transformation. And so the probability of getting that is E lambda. OK, so that's really, when we talk about quantum instruments, this is all that we mean. Right, so one important class of instruments is the measurement map, or the measurement instrument. So an example, the measurement instrument. Okay. And so right. So we have some instrument E1, E2. So this is, so J is a measurement instrument if each of the CP maps acts as follows. So when it acts on rho, what it's going to do is it's going to output tracing here. Where let's call this J hat. Is an instrument. Okay, so a measurement instrument is one of this form. So we've written down our CP maps, but the CP maps are very specific. Essentially what you do is there's another instrument associated with it, so we're going to call this J hat. And we perform this second instrument on our state. We trace over it, and what we get out is some index lambda. So the lambda are orthogonal the way to think of this is that we don't really care about our outputs of this j hat instruments. So we're going to trace it. We're going to trace over it. But what we do care about is the measurement outcome. So we don't care about the quantum part, but we care about the classical output.
J hat acts on the second system.
No. So okay, sorry. So this is j hat is it's like the underlying instrument. J hat acts on our system, and then we trace over it. So we throw away the quantum output, and then all we're left with is the classical information.
I'm trying to understand why it's necessary to define J and J hat separately.
Okay. I mean, I guess I wanted. It might be confusing.
Would it be?
Yeah.
I had a question in mind.
Yeah.
E lambdas don't have any kind of mutual orthogonality quality about them.
Yes.
They don't.
Right.
So the probabilities you write below there on the left-hand side are not probabilities for mutually exclusive outcomes.
That's right.
That you are building in.
That's what's going on here. That's why we add this index here.
That is why.
Just to add to that,
Yes.
in this case, for a given instrument, the output states are mutually commutative.
Yes.
classical states.
Yes.
In that sense, you mean they are classical states.
Yes. Yes. Okay. Right. Okay. So let's look at this here. So trace of E lambda hats acting on rho. Okay. Well, let's look at the Krauss representation of this E hat. Let's write this as m lambda k rho m lambda k. Right. So we can do this. And now when we substitute this into here, what do we get? We get that this is just equal to this. So we'll trace first. Trace of the sum of mk dagger mk. I guess there's lambdas here, right? Keep our subscript straight. Again, I just want to substitute this in here. M lambda k dagger m lambda k acting on rho. And so then what I'm going to do is I'm going to redefine this sum as, let's call this pi lambda. Okay? And this pi lambda is a positive matrix, right? Because each of these are positive, and we're summing up over positive matrices. So then we can write the whole thing as just trace pi lambda acting on rho. Okay, so now when we go back and we look at our measurement map, right, what this is doing is it's giving us, this is actually mapping to trace of pi lambda rho, and then we have, this is a number, so there's no real tensor right there. We have this, okay? And these pi lambdas are known as, this collection of them is known as a POVM. And each of the individual pi lambdas is a POVM element. Okay, so the point that I want to get across here is that for measurement instruments, it suffices just to characterize it in terms of these positive matrices here. Okay? All right, good. Because when we talk about state discrimination tomorrow and then the next day, we're going to be dealing strictly in this scenario here, where we just want to perform measurements that give us classical outputs. And so we're going to be dealing just with POVM elements.
Maybe you also want to emphasize that this is different from von Neumann measurement.
Yeah, right. Because the pi lambdas here, they don't need to be orthogonal projectors, right? You see here, there's really no restriction on what they are, except that this whole thing is trace preserving, right? But they don't need to be orthogonal. So that would be the von Neumann measurement would be if they were orthogonal projectors.
Who is the state of the system
Yes.
on which I want to perform the instrument?
You want to measure? Yes.
I want to measure. Lambda is the state of?
Lambda. This is just some index.
No, that
Yes. Oh, okay, yeah, this is your output. So you've input rho, and you've got out lambda.
This is like measurement apparatus.
Yes.
That's an answer now.
Yes, yeah. The reason I'm doing this is I just want to show how it fits under the whole quantum instruments formalism. Okay. Is that a question or stretching? Okay. All right. So that's the measurement maps, and then the last bit of technical stuff we need before we can move on is we want to introduce a topology on the set of instruments. Okay. So the goal is we want to talk about how close two instruments are. Right? And the way you do this is you introduce some distance measure. That's how you can be formal about talking about closeness. All right. So we're going to define the distance the following. For two instruments, first is J, and the second we'll say is tilde. The following we'll use to define their distance. So we'll say D, I'm going to put a diamond here, and I'll explain why I'm doing this, between J and J tilde is just the maximum tilde. Okay. Right. So this row now is acting in our two copies space of H. So row is in this pos of H. And what we're doing is we're saying, okay, we're going to input some state rho, and then we're going to compute the difference in the one norm between the pairwise elements E lambda in J and E lambda in J tilde. And we're going to sum up over lambda, and we want to compute the maximum. Okay, so we want to maximize over all possible inputs. And the operational meaning of this is that it gives us the best average guess for distinguishing J from J tilde. So, I mean, what do we mean by how do we distinguish two instruments? So you can imagine the following scenario where Alice and Bob or not Alice and Bob yet, but we're given some black box, okay? And what we know is that the black box is going to implement either J or J tilde. And our job is we want to guess which one it's actually implementing. And the way we're going to do it is we're going to send in some state rho. All right? But rho itself may be entangled with some separate system. This is why we have the identity here. So we're only going to act on one half of rho. And then at the end, what we get out is some state. And we're going to try to distinguish it between the two possible outputs. Either it went through J or J tilde. Okay? And the reason we're summing up over lambda is because we have a different number of possible outcomes. So when we sum over, we get the average. All right, so the reason we put the diamond here is this is inspired by something known as the diamond norm. If we just looked at, if we forgot about the sum here, this would be the definition for the diamond norm between two CP maps. Okay? So we have this notion of distance. And so then we can say that we can.
What is diamond now?
The diamond, right, so Let me just get rid of this here. So the norm between two CP maps, so say this is E tilde. It's given exactly by this.
Don't you want that rho is a state?
Yeah. Well, I mean,
So you mean the trace of rho? I mean, in the sense that the trace of rho should be 1, no?
yeah. Okay.
Which is stronger than
It's stronger than this, but it'll always maximize it. I mean, I guess you're right. This isn't wrong.
Rho could be a very high rank projector, then this trace norm will be much bigger.
Yeah, but then I would just scale. I would scale rho up.
I mean, it could be a projector,
Yeah.
which is not trace 1. And you have to scale it down.
Right. Right. Okay. Okay. Yeah.
You want the state.
Yeah. Sorry. Okay. Yeah. Sorry. You're right. Yeah. So we want this to be in our set of density operators. So what do we say? DH. Right. Yeah. Thank you. So whoever else caught that. Right. Yeah. Okay. Yeah. Again, in order for that interpretation to make sense, is that we're putting in some states, and so. Right. And this is just the difference of our two.
I think that private communication was important for the participants who should say what is it that you agreed on.
Here, when it comes out, the output. Yes. So say that again.
No, your private communication with Andreas, if it was important for the participants, probably.
Oh, I see. Well, sorry.
Okay, sorry, I thought I was shouting. Maybe you have to repeat.
Okay, no, the point was that I had originally written this as just any operator that is strictly, or is between 0 and 1, but as Andreas pointed out, it could be a projector, would satisfy that, and that wouldn't be normalized. And so then the interpretation wouldn't make sense because you're putting in some quantum states. And so you really want it to be a trace 1 object. You want to normalize this. I mean, it's even worse than that because you could you could increase your dimension and still satisfy that. Fair enough. Summary of your point, more or less. Okay. All right. Okay. So then with this notion of this distance measure, then we can talk about convergence of instruments, right? So we say that a sequence of instruments converges to another if their distance goes to 0. All right. Now, let's move on to LOCC instruments. All right, so the picture, remember I told you to keep in mind, is of this teleportation scheme. So here we have Alice. Something like this. Going on, etc. All right. And so the way we build up these LOCC instruments is that we suppose that the instruments are performed locally. And given the measurement outcome, it's broadcasted to the other party. So what I mean by locally is that if Alice acts first, okay, then we would describe the global instrument as we just tensor on the identity. right, so I'll put curly A here. Okay, so that the identity is on Bob's system there. All right, and now let's say she obtains outcome lambda. So I'm going to go back and forth here. So here, at this point, she's performing instrument. This is 1 there. And she learns lambda, and she broadcasts lambda to Bob. Okay, so lambda's going to go across the classical channel. And now Bob's going to perform some instrument, but it's going to be a conditional instrument. So then Bob performs instrument, and we're going to write it like this. So we'll say that's B1, so we'll give lambda, B2 given lambda. So this is what Bob performs locally. Now if we look at the global action, what is it? So the global action will be given by A1 tensor B1, lambda. Lambda, A lambda, B2, lambda, etc. Okay, now if you looked at this, this would not be a valid quantum instrument. Why? Because it's not trace preserving. Because it's only considering the outcome lambda. Okay, and so what we would need to do then is to recover the full instrument, is we'd have to index over lambda. So we would let lambda be 1, 2, etc. Okay. So a way to visualize this maybe is that in terms of a tree, there's just a very simple picture. So first, this will just be, suppose that Alice performs just 2 outcome measurements. So here's A1, A2. And when we refer to rounds of LSEC, this is what we mean. So this would be 1 round of measurement. And she broadcasts lambda. So and along this branch, it's outcome 1. And then Bob would perform some sort of instrument here. And likewise, along this branch, we have another instrument that Bob performs. But again, it'll depend on Alice's outcome. Okay. So now what we do is we build this up, right? So we let this go on round after round after round. And probably a way to handle this, so it doesn't get a bit crazy, is if we index like a vector notation. So let's see. So I'm going to let ij. This will be measurement outcome in round J. Okay, and then we can consider a full sequence of measurement outcomes. We can write it as a vector. So this would be I1, I2, I3. And let's say this goes on for R total rounds. Okay, and so then if we would write it out in terms of the CP maps, this would look like the following: I2, R minus 1, R minus 2, let's say. So again, Alice is going to be the first to perform, and Bob's going to be the last to perform, like this. So this is the IR. This would be IR minus 1. So this is the action in the last round. But now we want to concatenate it with all the previous actions. So we want to compose it. So this is going to be composition here, going all the way down to a I1, tensor B I2 given I1. Okay, so what I mean by the circle here is composition. So we have a sequence of compositions going on. Is that clear? Everyone, question? Yeah. I was writing out a room, so maybe if I write it out better. Okay, so we'll build it up like this. So first, Alice measures. She gets outcome I1. Okay. Then she broadcasts to Bob. Bob makes some measurements, and he gets outcome I2. Okay. Now it goes back to Alice, and she performs another measurement. She gets outcome I3. But I mean, we're thinking of this like sequentially, and this has happened after she's already performed I1. So we have to. I guess I can. Well, I'll write it like this. So this would be I3 given I1, I2, right? And now it goes back to Bob, and then Bob's total action will be now B I4 given I3, I2, I1, and then B I2, I1. And then you keep going on, et cetera. And so then you can think of this as just composing layer after layer. Right, so the next one would be Alice would get some I5 given all the rest going on. And so then in the end we can notate all the outcomes with some vector I, and we get this. So who asked that question? Yeah, is it clear a little bit? I mean, the thing is, it gets unwieldy because you have all these outcomes. So the notation is a bit much. Okay. So then we can maybe write it a bit more cleaner. Is we write the instrument L is just say AI tensor BI, and now this is some sequence, and it's over all possible outcomes. So this is I1, I2, I3, etc. Okay, so this is it. Right. All right, so I mean concretely, if we looked at the tree, then we would have, in that sequence, we would have 4 possible outcomes going on there. All right, now there's one more thing we want to add to this, and you can imagine that after Alice and Bob have performed their measurements and they have all their different branches, maybe they're not really interested in the details of every possible outcome. Right? So maybe they were trying to perform some sort of operation, and let's say that this branch and this branch was a success, and this branch and this branch was a failure. Okay, they're trying to do something, and if they have either this outcome branch or this outcome branch, it's a success. Otherwise, it's a failure. So the way they would handle this is that they would perform a coarse graining over their measurement branches. Okay. Again, they're really not concerned whether or not it was this outcome or this branch. They just want to know whether it was a success or a failure. And the way you handle coarse graining is you just sum over the different branches. So in this case, let's say we summed up over this branch and this branch. Okay, so maybe if we had 2 colors, it'd be good. But so it's this branch, the success and the failure branches. And so what's this going to do? Well, let's see. So originally, before we coarse grained, coarse grain. I'll write it out. Coarse graining. So fine graining, you can think of this as being a very fine graining because it's all possible outcomes. And then coursing, you just bin them together into certain bins. So we'll look at this example here. So the original map, or the original instrument, was, so it would be A1, B11, A1, B21. It's a four elements instrument. A2, B21, A2, B22. Right? So there's 4 possible branches, 1, 2, 3, 4, corresponding to 1, 2, 3, 4. And now we want to coarse grain. So I'll put CG is coarse graining. And the way we do it is we just sum up over the branches that we want to coarse grain. So this would be some j tilde. And all right, well here we wanted branch 1 and 3, so then it's just the sum of that. So it's A1 tensor B11 plus A2 tensor B12. So this is one outcome, and then the next one would be A1 tensor B21 plus A2 B22. Okay, so all we've done is we've just discarded, or we've sort of thrown away. We've lost some information because here this was fine-grained. We had all the information of every possible outcome, and here we've just grouped it together. So if we know that this outcome happens, we don't know whether it was this branch or this branch, but we don't care. We just want to know whether it was a success or a failure. All right, so what we do then is in LOCC is we allow for this overall coarse graining at the end. All right, and so what that'll do is that'll take L and it'll transform it into something of the following form. So we're going to take a partitioning. So we're going to, of all the numbers, all the integers, we're going to partition them into disjoint sets. Yes?
So you have considered here all these outcomes are coming with same probability?
No, not at all. There could be different probabilities. Yeah, each branch has a different probability of occurring. Right, and so then if you wanted to compute the total probability of the branch, it would be the sum of the individual branches, right? Okay, so now when we perform a coarse graining over this instrument, what we get is, call this L tilde, and this will have the form, so let's say this is I in S1, AI, BI, and then we'll have another set called S2. So essentially what we've done is we've taken all of these fine grains, and we've thrown them into different bins. And we've enumerated the bins by S1, S2, S3, going on, et cetera. Okay, so we've performed this coarse graining here. Each B? Okay, well, right, so the way I'm notating this, you're right. I mean, if you unpacked it, yes, they would all have superscripts, yes. But for clarity, okay. Right, okay. And so this is the final, most general form of an LOCC instrument. Okay, so again, we assume that this went up to R rounds. So we assume that this terminated at R. And so this is the most general R round LOCC instrument. Okay. Right, and so then what we say then is, when we define what LOCC is, we're going to define it as the union of all R-round protocols. So what our LOCC R is, these are R-round LOCC instruments. And then LCC is the union over all possible rounds. Okay, so this is our definition of LOCC. Okay, you can see that this, just looking at this, is a very complicated set of instruments. First of all, because R is unbounded, right? So if we really want to consider the full class of LOCC, we have to consider protocols that go on for an unbounded number of rounds. Yes?
Can one also write LOCC is equal to LOCC subscript infinity? I mean,
I think I do, and I'll get to that in a second. Because when you write infinity, you're implying some sort of convergence. And so this is why we'll get to that in a minute, okay? But that's a good question. All right. But one thing I just wanted to point on before I touch on that point or that question. So this we said was the most general LOCC instrument was of this form, where this whole thing is trace preserving. Okay. But you can imagine that maybe we don't want to be trace preserving. So we're going to relax that assumption. So if, let's say we have L of this, well, I'm not going to write it again, but so if L is not trace preserving, then we say that L is a stochastic LOCC instrument. Stochastic LOCC instrument. And we denote this, or abbreviate this, by SLOCC. So you'll see this a lot in the literature. They talk about SLOCC transformations or SLOCC equivalences. What this means is that you're able to go from one state to another state by some sort of instrument that is not trace preserving. So meaning if it's not trace preserving, that means that you're discarding some particular outcomes. This is a process known as post-selection. So you're only concerned about certain outcomes. That's what you're deeming a success. And you'll get those with some probability. That's why it's stochastic. But with some probability, you won't get them, and then you fail. OK, so this is first point. The second point I wanted to make is that, right, so instruments of the form so here we're going to sum over let's say this is I don't know, we'll call it S1, sorry. And this will be I's in S2. Etc. So here what I'm going to do is I want to drop the constraint that these AI and BIs are built up in this way. Okay? All I'm going to do is I'm going to look at this and I'm going to say, hey, this has some particular structure to it. And the structure is that it's a sum of product CP maps. Right? And I mean, in the LCC situation, it has much more structure. The structure is that it's built up in this particular way. But here, we're just saying, well, if it just has this product CP structure, this is known as a separable. Instrument. Okay, and so you can see that these are believably more easy to analyze because again we've dropped this restriction that we must build up the CP maps in this way. All right, those are just two quick points. We'll say more about separable instruments in a little bit. So how are we doing on time? Am I over or am I under?
Yeah, nearly. I mean, you can take a few minutes and stop at a convenient point.
Okay. Oh, wow.
We started a couple minutes late.
Yeah. Okay. Well, I wanted to talk about this convergence question. Okay. Well, maybe maybe I'll just talk about the convergence, and then we'll be done, and I can. Yeah, it'll be a natural stopping point. Okay. Right. So. Again, this set here has this property that we can consider unbounded rounds, protocols where R is unbounded. And so what we want to consider then is the closure to this set. right? Because if you look at this, this doesn't look like it's a closed set of instruments because we have this unboundedness property. So we define LOCC closure as the set LOCC plus all its limit points. Okay, and we'll just say and. That makes sense. Okay, so the limit points in the following sense of remember we had this notion of convergence where we define this norm over instruments, and so then we say that. So if we have a sequence of instruments now. So this is some sequence of instruments. Sequence of LOCC instruments. I mean, there's a few ways this could happen. You could think of this as being a 1-round instrument, a 2-round instrument, a 3-round instrument, etc. You don't need to think of that way. We just have some sequence of instruments. And we say that it converges to some instrument called this L bar, meaning that in the limit as n goes to infinity, if we look at this distance between L and L bar, this goes to 0, right? So if it converges to L, then L is a limit point, of LOCC. And so then it would exist in this closure set. Okay, and what I've been involved in the past few years is studying the difference between this closure and just LOCC and its closure. And what we found is that actually they're not equivalent. And so what does this mean physically? Okay, well, I mean, what this says is that you can there are certain sequences of protocols, measurement sequences, transformations, that are getting closer. They're converging to some point L, but yet you can't implement this by LOCC. So you can get closer and closer to performing some particular task, but you can't actually perform that limit task. And so I think that's sort of a curious property of LOCC. Okay, so this was maybe a natural pausing point, stopping point. So,
And would you say it's a useless operation, LOCC?
is it useless?
LOCC bar.
No, actually, on the contrary, I think it's the more natural thing to consider for the following reason. So, if you imagine actually performing an experiment, then you always have some sort of error in your experimental apparatus. So it only makes sense to consider sort of an epsilon bound around what you can do, and that's exactly what this bar gives you, this LCC bar. Yeah.
You're going to get error bars of that.
Yes. Yeah. Right. Okay. So then I guess in the afternoon, if you have more questions, we can discuss or whatever. We're good. Thank you.
Can I ask a quick question?
Yeah, sure.
Yeah. Every LOCC has CP map.
So as a CP map.
Yeah.
Yes. I mean, well, we think of it as like in this instrument, it's a sequence of CP maps. But yeah, it's definitely a CP map.
Every LOCC is a CP map.
Yes.
And then, given a CP map, I will be interested
To know whether you can.
whether it is an LOCC. In that case, that union seems to be indefinite because how to understand.
Okay. So right. Well, maybe I guess I can say the following is that if we write global, right? This will be the set of all CP maps you can perform. So this is the global operations. Then we know that this is closed. Okay. So, and actually, when we talk about these separable instruments over here, that class is also closed. So really, this non-closure bit only comes in when you demand your instrument to be built up by this sort of classical communication back and forth.
So
measurement.
every separable CP map is LOCC. Right?
No, that's not. No. We'll see an example. So over the next 2 days, we're going to look at examples where this instruments of this form cannot be implemented by LOCC.
But I think my question is, see, given a CP map,
Yes.
I can see whether I can write it as a sum of product CP maps. When given a bipartite CP map, two-party CP map.
Yeah, I don't know. That doesn't seem easy, though.
Pardon?
That doesn't seem easy
No, it's not
because
easy.
this is like the
I mean,
separability
I can
problem,
ask-
right?
No,
Okay.
I don't want to answer that question completely.
Yes.
So if I have a CP map, would
Yeah.
I able to write it as a product of CP, sum of product of CP maps?
Yes.
Then I will be interested to know whether raise questions like, does it correspond to an LOCC, in which case this union looks intimidating. Now, how do I understand this union, as a sum? Or there you have written script J as a set.
Yeah. Yeah, okay, so I mean, you think of this LOCC-R as just R-round protocols that terminate after R rounds.
That's okay.
And so then we want to say that we want to consider all possible.
What is the CP map corresponding to it?
The CP map, well, it's, I mean, we think of it as an instrument. So it would be whatever you built up in this, the way I was describing. So for each of those elements in there, you would have to build it up in terms of this protocol of
See,
back and forth.
Every round, for
Yes.
every round it is a CP map.
Yes.
No, but you should think of it differently. There are those which can be implemented in one round. There is a bigger set that can be implemented in 2 rounds. There is another bigger set that can be implemented in R rounds.
Yeah.
LOCC is that which can be implemented in R rounds for some integer R. That's the union. It just means there is some R such that it's R round LOCC. You get more and more maps. You don't modify the maps. You get just new ones. Things that you couldn't do with R minus 1, now you can do with R. Because you get more and more complicated procedures, no? It's ping pong protocols. So it's intimidating, yes, for sure. I guess we can say that for fixed R, you can test whether you can formulate a condition, a finite condition.
It's computable, I guess.
Yeah, computable. For finite R, you can formulate a condition that in principle you can check, even though it scales very badly with R. But this union is very difficult indeed.
Yeah. Okay. Very good. Thank you. Yes. Sorry? Oh, the mic.